Hello. In this episode, I will show you how to request GPUs from your Flyte task definition and what configuration is needed in your infrastructure to make it work. So, first of all, how it works in general. We will see different use cases, but this is the general case. So when you request a GPU resource, the first thing that happens in general is that your workflow definition is compiled into protobuf format. This is performed by Flyte itself, and the output is a serialized format that is programming language independent. Most typically, you're using the Python SDK from Flyte, but it could be any other language. It will be compiled into protobuf. If you're curious, this happens, let me show you, probably right here. This is done by the Flyte IDL component. In the Flyte repo, you will find a folder called Flyte IDL, so you can explore all of this if you're curious. This particular section here will take the GPU accelerator config and it will add it to the whole task definition or the workflow closure that gets stored in S3 or the blob storage you're using, right? So that's the first thing that happens. It gets compiled, and then the missing piece between Flyte and Kubernetes, because up until here, this is not Kubernetes specific. The workflow definition is compiled, but the component that translates this into something that Kubernetes can understand is Flyte Propeller. This is a controller that follows the operator pattern and that will instruct the API server, Kubernetes API server, with the specific pod spec that it should use for each task execution. Remember that at least by default, every task execution in Flyte renders as a pod, as a Kubernetes pod, and every pod needs a spec. So Flyte Propeller will instruct the API server to configure this pod. And plus, in this case, in the case of GPUs, it will inject something that is called toleration. The toleration is like a whitelist type of configuration for Kubernetes to make decisions on where to run pods, right? So if your Kubernetes nodes, the worker nodes, have configured a taint or a whitelist, let's say, of which workloads are allowed, only pods that have a matching toleration will be accepted to run on these pods. So this is pretty much the case when organizations have GPUs on their environment. They will try to use at least this basic scheduling control mechanism to make sure that only workloads that truly need a GPU will run there. So by default, Flyte Propeller will inject a toleration to make sure that this is the case, and it will support your scheduling constraints. I will touch a little bit on this presentation. Then the Kubernetes API server applies the pod spec, including the toleration, and then the scheduler will see if there are nodes, or at least one node with available resources and a matching taint or a matching configuration to finally run the pod there. That's it. So probably there could be different questions. One of it could be, okay, how the Kubernetes API server knows that a particular node has a GPU, or that a particular node knows that certain GPUs are in use and others on other devices are free. So this is pretty much controlled by the device plugin. This is a Kubernetes mechanism. Let me show you real quick here in docs. And this is the mechanism as of today. This is going to change in the future, but as of now, it uses device plugins. For example, NVIDIA has one that gets installed into your Kubernetes cluster, and it will advertise to the Kubernetes API server the accelerators. How they get advertised? They are advertised as extended resources. There's no, at least not now, a particular category for GPU accelerators. It's more an extended resource, and in Kubernetes, an extended resource is anything beyond CPU and memory. The docs, the Kubernetes docs here use the example of a USB dongle, just to illustrate that, yeah, this is not your regular CPU and memory resources. For storage, there's a whole different controller, the container storage interface. But this is for anything beyond CPU, memory, and storage. Right, so in summary, the device plugin will advertise, hey, this node or this set of nodes has an extended resource, in this case, a GPU or a set of GPU accelerators of this model, this capabilities, etc. It will advertise this to the API server, right? And what Flyte Propeller does is to inject the configuration necessary for the scheduler to understand, hey, this pod requires this specific device or this set of devices, right? How specific this can be, we will see this in the use cases in this session. Something that is very important, just to close this idea, Flyte Propeller inject tolerations, but that doesn't mean that your nodes require a taint. We will see here that even for nodes without many taints, without most of the taints, that will match the tolerations injected by Propeller. Even so, the workflow execution runs without problem on GPUs, right? And that is because, again, this is kind of a wide list. The taint, or let's say the analogy will be a key and a lock. The lock will be the taint, and the toleration will be the key. You can have the key, but if there's no lock in the door, okay, that's fine. But you have the key in case the door has a lock. In case the node has a taint, your pods have toleration. Okay, so first use case, request a GPU with no device preference. So the only thing you need is to add this configuration to your task decorator, instructing Flyte to request a GPU. It could be 1, 2, 3, etc. But in this case, the important part is that it's a generic device. We are not specifying which model, which type of device. We just need this task to run on a GPU. Reminder that it could be that this task is part of a workflow with more tasks, with multiple tasks, and only this particular task run on GPUs, or only this task needs a GPU, right? It's not like if you request this for a task, the whole workflow will run on a GPU. That's not the case. It will only be this particular task, okay? And I'm using here in the example the Kuro is available method from the Torch library, just to check if there's a GPU available. It will return true in case it finds a GPU in the node. Okay, so I will run this. I'm running Flyte on Azure Kubernetes service. By the way, if you want to do this, you can go to the deploy Flyte repo. I will leave the link in the description here in the video. And in a couple of commands, you can go from an empty Azure resource group to a fully working Flyte deployment, including ingress, TLS, and everything. So I'm using this just to have a production grade environment where to run this stuff. And also this set of Terraform scripts or OpenTofu, you can use either one. Also automate the labeling that is necessary for the Kubernetes nodes, right? So probably by the end of this session, you will understand this a bit better. So I will show you the code real quick. So a couple of things. Let me change this to be actually a generic request. There you go. Okay. So here, just focus here. This is the generic request, a single GPU with no specific model. What I have commented out here is the image spec configuration. What is image spec? This is a Flyte feature that actually builds a customer container image in a very simple way. I mean, you don't need to create a Docker file. You just need to declare what you need in the image, and Flyte will use MVD to build containing image for this workflow. I've been having some issues with Azure Container Registry. I'm not sure if it's about the size of the Torch library or what, but I ended up using a Docker image or Docker file, regular Docker file, and if you need it, I can just post the configuration of this image. Very pretty simple. I mean, it's the same base image and just installing the PyTorch package or Torch package. All right, so when I run this, I'm using PyFlyte Run. PyFlyte Run is a way to do multiple things in a single step. First, it will take your code and say push it to Flyte admin to be compiled. And after it's compiled, it's registered to the Flyte admin server and it's executed. All of these 3 steps in a single command. There are commands in Flyte for these separate steps because many times you need the workflow iteration to be compiled and registered, but not executed right away because you want to execute it on a schedule or something, or via CI/CD system trigger, etc. So you can do it separately. But for this example, I'm using PyFlyte Run that will do everything at once. I'm using -- remote because this is a remote Flyte cluster. It could be local, meaning that you will run your code in your local Python environment, which is great for testing, not having to spend cloud resources. But this is remote, and I'm using an image different than the default base image that Flyte uses. I already pushed this image to my Azure Container Registry. Yeah, I'm just calling the name of the task definition and the check torch function, right? So will take not very long, hopefully. And yeah, I have enabled deep level of logging, so that's why it logs a lot of stuff here. But it's running now. It seems to be at least compiled and executed, or at least registered. I'm not sure if it's running yet. So before going to the UI, I'll check from the Kubernetes point of view what's happening. And I know that there are many options. I mean, for to have a UI for Kubernetes, but I typically prefer still the CLI. So seems like already completed. So I will see how it configured the actual path, right? So I need to specify the namespace. This is basically a project and domain combination. Oh, yeah, Git. How genius. No, Git probably doesn't know about this. It's K. This is an alias for kubectl or kubectl. Or, okay, so multiple things here. Again, I could have used JSON query to kind of filter down the relevant fields, but just wanted to go straight to a couple of things that are interesting here. See that this pod has a toleration injected, as we mentioned. NVIDIA.com/GPU. And if this toleration exists, I mean, what it means is that if a pod is already running and didn't have the toleration, oh, don't do anything. But if the pod is about to run, it needs a decision from the scheduler, and the scheduler cannot find a node with this toleration, do not schedule the pod, right? It will stay on pending state, pending on finding a node with a matching taint. That's what this toleration means. So this was injected by Flyte Propeller. What if, I mean, what is the source of this name, NVIDIA.com/GPU? This comes from the device plugin, right? This is the resource name that is, in this case, the NVIDIA device plugin or advertised to the Kubernetes API server. If for any reason your devices advertise a different name, you can actually instruct Flyte to use a different name. In the Helm chart, the Kubernetes, the Flyte documentation and the GPU configuration section that I will also put in the description of this video uh, shows you where to change this single line and for Flyte to use a different resource name. Right, so nothing else. So that's it. And apparently it already worked. Already finished. Yeah, 3 minutes ago. And I can see here that check torch, the output is true, right? We can also verify from oh, sorry, from Kubernetes that if I get pods and I say output wide, I can see here that this pod that just run 3 minutes ago was scheduled on the GPU pool from the Azure Kubernetes service cluster where I'm running this, right? So why it work? Well, the only thing you needed in the infrastructure side or in the Kubernetes side was to have the nodes, the GPU nodes with a matching taint. So let me see. I'll describe this node again without using JSON query, just going straight to the full config, but I will show you here real quick the taints. It has a matching taint, nvidia.com/GPU, now schedule. This was automated by the Azure reference implementation, or the Flyte on Azure reference implementation that is in the deploy Flyte repo. But depending on the process your organization uses, the idea is that in the end, this should be the case. It should have a matching taint. And this was the first case, generic GPU device request. Second use case, this is now requesting a specific accelerator. So you can see here that I'm importing a constant, in this case, a V100 for the NVIDIA Tesla V100 device, and I'm requesting here the accelerator to be a V100. So what is the source of this constants? What constants are supported? Can you use? This is declared here in the specifying accelerator section, the docs. There's a list of the supported constants. I mean, supported now by Flyte Kit. Probably in the future, we'll need to add more devices, etc. But right now, this is the list. So you should do the import that is coming from here. It could be a V100. It happens that right now I only have a single cluster. I mean, I'm GPU poor in some ways. So I only have a single cluster, a single node with a single A100. So I can only show you that. But from the accelerators module, you will import the constant you'll need. In this case, I can show you the A100, and I will request here the specific accelerator, the A100, right? Cool, so let's run this version and see what happens. All right, so check the pods. Cool. Yeah, a couple of seconds ago, and this one is running. So see, that means that the scheduler was able, whatever happened in the background, was successful because it's not impending or crash loop back off state or anything like that. But in this case, probably the most typical or common kind of behavior will be to, if something is missing in the configuration, it will be left on pending state, right? It even finished already. So for this, I will need um, more than what the scribe provides. I will need the full spec of the pod in YAML format. So I'll get exactly that. So a couple of additional things that happen here. First, you can see here that there is the nvidia.com/GPU toleration. That's kind of the base toleration, and this is a good idea. Again, if you have in your Kubernetes clusters nodes with GPUs and nodes without GPUs, this is a lifesaver, especially considering the cost of GPUs these days. So it will always, oh, every time you request a GPU, it will always insert this toleration. But now that I specify the model, it added an additional toleration that says if there is a taint, if there's a taint specifically for workloads that require an A100, okay, this is the configuration of the toleration for the scheduling to work. Again, remember uh, the analogy between the key and the lock. This is the key. If there's no lock in the door, that's fine. But if there happen to be a lock in the door, it has to match this configuration. But most typically, what dictates this configuration is what your platform team has already configured in the GPU nodes. So that means that you can change the key part of this. I mean, this is the key value pair, right? So the key here is arbitrary. You can use whatever your cloud provider supports, whatever your platform team let you use. You can use it here. You just only need to instruct Flyte to let Flyte know what key are you using for the taints, right? And again, the Flyte documentation show you the specific uh, line of the specific section in the Helm chart where you will instruct Flyte, hey, this is the key. When I'm using a specific device, this is the key for the toleration I'm using. The value is not arbitrary, right? The key is you can use whatever your platform team decides to use, but the value is not arbitrary, right? This comes, I mean, this comes from the code. These constants translate to a kind of full device name, and this is in the Flyte kit code. Let me see if I can find it. Yeah. Thing here, this is all in the again the reference implementation. See. There you go. So you can see here that, for example, for the L4 or the, I don't know, the P4, right? The actual device name in this NVIDIA Tesla P4. And this is what you have to use as the value side of your taint in case your platform team is tainting the nodes. This is what you have to use, okay? And that's one side of it. And also another thing that happened here, which is different to a generic GPU device request, is that Flat Propeller injected a node affinity. And this is a more opinionated mechanism, Kubernetes native mechanism to instruct the scheduler. Okay, probably, yeah, you don't have this whitelist, blacklist kind of approach of taints and tolerations. That's fine. But the node affinity takes this a step further. Okay, Kubernetes scheduler, I want this pod to run on this specific type of node. Okay, what is the criteria to select the node or the nodes to run this pod? Okay, in this case, it's every pod, every node, every worker node that has a label that matches this configuration, a label with a key GPU accelerator and a value NVIDIA Tesla A100 in this case. if the node has this label, okay, this is the node where I want to run this path, right? So again, the scheduling becomes a bit more constrained and more specific. And this is good because, yeah, A100s are not cheap. So with this in mind, the reason this execution work, it's probably because besides the tame, which is optional in this case, uh, probably the node already has the label. So let me check. Um, and yeah, that is the case. NVIDIA.com slash GPU accelerator. It has this label. This was again automated by the Terraform scripts in the deploy Flyte repo. Uh, so this label is necessary here, right, for the scheduling to work. Again, reminding that I choose this key because it was similar. I mean, follow the same structure as other base configurations created by the NVIDIA GPU operator in this case. So I use GPU accelerator. But I had to use this specific value because that's what um, Flight Kit or Flight Propeller in this case will insert in the pod spec as you saw, and that's not configurable. Um, and only if it matches what the nodes have, the scheduling will work, right? So this is the configurable part, and this is the not configurable part, right? Okay, so what devices are supported by FlightKit with the A100s plus all of this, B100, T4, B100, etc. All of them are supported by FlightKit as of today. Cool. Now a partition. The A100 is a special device because it's part of the pair family, which supports multi-instance GPUs. It's basically a way to mm, have a logical separation of resources and make sure that to enable a more optimized use of the precious GPU resources. So these partitions have specific configurations. Let me see. Yeah, there is a blog post, and there's also the user guide from NVIDIA that will show you the supported profile names or supported partition configuration for the A100. So I'm using here in the example the 2 gig.10 gig profile name, which means basically 2 slices of streaming multiprocessor uh, resources and 10 gigs of memory, which is to 10 to 8 of memory and 2/7 of the streaming multiprocessor instances. Okay, and I'm specifying here in the task decorator this configuration, so I will go straight here and yeah, this is, yeah, dot partition. Nice autocomplete will show you the supported profiles, which comes from what NVIDIA supports. There you go. All right, nothing more. From the user perspective, this is all you will need to do, and this is good for resource optimization, making use of multi-instance GPU. So again, I will run this and see what happens, especially from the Kubernetes side. Cool, because the previous execution, I didn't even check, but the previous execution, yeah, this is the current execution, but the previous one also worked. The output was true. So this, all right. So if I go here, yeah, it already complete. So I will get the full spec of the pod and see what's inside. What's different now? So again, there will be a base toleration injected, nvidia.com/GPU exist. This is the base one. There's the previous one. Hey, only nodes with NVIDIA Tesla A100s. And only nodes, this is again optional. I mean, this is to further control scheduling. If you want to even taint your nodes with the specific partition sizes that are admitted or supported, that's fine. And Flyte supports this. If you don't want to go that specific in the, at least in the node taint configuration, it's fine. But from the Flyte side, the configuration is there. Um, and the other thing that happens is that the original node affinity is there, but there's an additional expression. Okay, only nodes with a label that indicates, hey, this is the partition size. And only nodes with this label will be accepted by the scheduler to run this pod in summary, right? And again, this execution worked because my single GPU power node has this configuration available. GPU partition size, there you go, here it is. Right, it was labeled again, this was automated by the Terraform scripts, but the label is there and that's why it worked. Okay. Right. So yeah, there are a couple of additional use cases when you can request the full resources of an A100 for a specific task. If that's what you need, you only need to append that unpartitioned, right? And it will run in the entire A100. In this case, it will insert an additional toleration that you can or you cannot, if that's up to you or your platform team to decide if you want to configure a thing for this. And there will also be a label inserted for this. And you can also request an A100. That's what I just did, an A100 with no partition size preference, uh, but Flyte Kit by default. If this is the case, and the reason this worked and didn't complain, hey, you didn't specify a partition size, it's because Flyte Kit uses this profile by default, the two SM instances plus 10 gigs of memory profile that's used by default, right? All right. So just to recap, so a single annotation is all you need in Python decorator to request GPU resources. I show you the requirements that your infrastructure needs for this to work. Mainly is about labeling, and especially when you're requesting anything beyond a generic GPU. When you're requesting specific devices or partitions in the E100, you will need at least labels, and you can have also taints. But the final scheduling decision is handled by Kubernetes, and this is still the case as of today. And remember that for optimal accelerator resource utilization, Flyte supports multi-instance GPU partitions. So some of the future work, how to support TPUs, for example, other kind of inference chips like Trainium or Inferentia from Amazon. I've seen folks using Flyte with TPUs, but using pod templates. They had to rely on pod templates, and the pod template, you can specify the resource name and all this, because as you saw, the current implementation is more or less inclined towards NVIDIA GPUs. But for other types of inferencing chips, folks have had to use pod templates. So again, if you feel you could contribute to this, making this more generic, more universal implementation, please do it. And also the rise of dynamic resource allocation in Kubernetes. And I invite you to go to the Kubernetes docs and read about this feature, which is right now is in alpha state. And I think it will move to beta in the upcoming 1.31 release. Probably by the time you watch this video, it will be already on GA, and the idea is it will supersede device plugins, because as you saw, the fact that you're using the same mechanism to advertise and manage GPU accelerator resources, the same mechanism for a USB dongle, doesn't make more sense. I mean, they have very different scheduling needs. So the idea of the dynamic resource allocation is to give the Kubernetes scheduler more visibility, more control on how to schedule available resources, available accelerator resources, and that will, when this goes GA, probably this will trigger changes in the backend implementation in Flyte, because right now we make use of what is stable code in Kubernetes, which is the device plugins mechanism. All right, so if you have any question, please drop it here in the comments in the video, or go to slack.flyte.org. You can find us there, you can find me there. Any question you may have on GPU accelerators, please drop it there. So thank you for watching.